Hi, linear algebra students. We are in 3.3 applications, sorry about that, of determinants. And we're doing an example that's related to Cramer's rule, and it's certainly in your reach. You should do this example by yourself and watch the video just to confirm your work, okay? So for S, for like a parameter S, we consider the system given like this. Okay, so keep like let's just underline where these S's are. So there's one here and one here. And we're asked two questions. One of them is, for which values of S does this system have exactly one solution? Okay? And second, for these values of S, use Cramer's rule to describe the solution. Okay, so part number one is going to be quite quick. It's just an argument with the invertible matrix theorem. So, all right, let's do it. So number one, the idea is to realize that the system can only have a unique solution if the matrix is invertible. So, the system can have so actually for the system to have a unique solution, for the system to have a unique solution, its coefficient matrix, and let's call it A, but you know what is A at this point of the semester. So its coefficient matrix A, matrix A must be invertible. Okay, this is part of the invertible matrix theorem. Unfortunately, I don't remember exactly. I actually could find it in our book. It's not, so it's, I know the page by heart. It's 114. So if you take your book at page 114, you're going to see, there you go. It's basically a statement, D, and it's like G as well, implies A. Okay, of the invertible matrix theorem. Okay, so do like me, right? Read in your book which statement it corresponds to, but it's basically the one that says like if A is always consistent and A has only a unique solution, then the matrix A must be invertible. Okay, it's part of the invertible matrix theorem. But in this section, we saw a new statement, part of that invertible matrix theorem, is that if A is invertible, it means that its determinant needs to be 0. Okay, so let's actually add this. And determinant of A must be 0. Must not be 0. Must be non-zero. Okay, I have to be very careful about what I say. But there you go. Okay, so so obviously then we know that A will be equal to the coefficient matrix here. So it's going to be 3s, -2, -6, and s. So taking the determinant, so the determinant of A, so very simple determinant, but I always like to do this, like you know me at this point, right? I like to put colors on the whiteboard. So here you are. So you're gonna have here the main diagonal is gonna be 3s squared. And the off diagonal, just be careful, there's a lot of signs, but it will end up being negative, and it will be -12. Okay. And at this point, obviously, it's just to factor and see what you get. So, all right, let's factor out a 3. So we'll have like s squared minus 4. So 3 times s minus 2, s plus 2. And basically that gives it to us because the determinant is not equal to 0 when s is not equal to negative 2 and s is not equal to 2. Okay, so this is the answer for number 1. What I'm going to do now is I'm going to just take note of it. I don't think I will actually need this information, but just in case, because I'm going to erase all of this. So, all right. I'm just going to write here s is not equal to negative 2 and s is not equal to 2. So now let's erase all the blue. And we're doing number 2. So for number 2, what's important to realize is what is the vector b? Well, the vector b, let's color code it in red. No, not in red. Let's do it in orange. Yes. So this is the vector b. Okay. So yeah, and let's actually copy down what each of the vectors are, right? So you're gonna get. I'm not gonna color code A1 and A2, but we have that A1 is 3s and 6. Okay, A2, which is the second column, obviously, is negative 2s. And finally, B, like the orange vector now, that's going to be equal to 4, 1. And what we have to do is to compute all of the ingredients. So, first step, we calculate what is the determinant of A1b. So determinant of A1b, which you should remember, is the determinant that you get by replacing the first column of the coefficient matrix by the vector b. So it's going to be 4, 1, and then the second column you just leave as is. So negative 2s. And then, obviously, the calculation will give you here 4s minus negative 2 times negative 1. So in other words, plus 2. Okay. Let's also factor this just for convenience. We're going to get twice 2s plus 1. The second ingredient is obviously the determinant of A2b. So very similar, but instead you replace the second column by the vector b. So you have like 3, 6 and 4, 1. And same method of calculation, right? This is just 2 by 2 determinants. So we're ending up with 3s. So there you go, 3s. Okay, minus 24. And again, let's just factor the 3 out of convenience. We will get s minus 8. And now something that I unfortunately erased is the determinant of A that we need as well. Okay, so and we saw it in number 1. So the determinant of A, recall, it's our 3 times s minus 2 times s plus 2. Okay, just note that it's from the number 1. So, all right, we're ready to use Cramer's rule now. So, Cramer's rule. Cramer's rule, recall that x1 is going to be equal to this determinant. So, det A1b divided by the determinant of A. So in other words, well, it's going to be this. So 2 times 2s plus 1 divided by 3 s plus 2 times s minus 2. Oh, I'm actually just going to write s minus 2, s plus 2. Like this. Okay. Obviously, x2, and I'm going to write it over here. Unfortunately, I'm going to have to work a little bit more vertically. So the determinant of A2b divided by the determinant of A. So this is going to be, actually, notice here that there's a factor of 3 that will cancel, right? So let's just not write it in the final answer. We will get s minus 8 divided by s minus 2, s plus 2. So this is our final answer to number 2. All right, I hope this helped. So see you in class or in the next video.